going to talk about multi-pass Kirby lower bound for approximating math cut. This is joint work with my advisor Dor Minzer and fellow student Shuo Wang at MIT. So we'll first introduce the mass cut value of graphs. The mass cut value of a graph is defined to be the maximum fraction of edges in a graph that can be cut by any bipartition of the vertices. So in one extreme case, if we have a bipartite graph, then the natural bipartition of the vertices cuts all the edges, so giving rise to a mass cut value of 1. If the graph is close to bipartite, then the mass cut value is close to 1. And in a complete graph, any bipartition cannot cut significantly more than half of the edges. So the mass cut value is approximately 1/2. And we observe that in every graph, the mass cut value is at least 1/2 because a random bipartition cuts at least half of the edges in expectation. So the algorithmic task we're going to care about in this talk is of estimating the mass cut value of graphs. We know that for every graph, the mass cut value must lie in this interval, and there's a famous Gomez-Williamson algorithm that runs in polynomial time and gives a 0.878 approximation, and it is under the unique games conjecture, it is NP hard to do better than this ratio. So in other words, the best we can do in polynomial time is to given an input graph is to pin down its mass cut value to an interval whose left endpoint and the right endpoint has a ratio of 0.878. And we're going to talk about the model of multipass streaming. Multipass streaming is similar to a usual Turing machine model. The input graph, the edges of the input graph is given in a sequence on an input tape, but the difference with the Turing machine model is that the tape head is only allowed to go in one direction and for about constant times. So this is the access that is allowed. And usually the Turing machine is assumed to have a sublinear space bound. So sometimes we usually assume that it's maybe polylog than memory. And we want to talk about space lower bound in this model for approximating math cut. It was proven by Kapralov, Khanna and Sudan in 2014 that distinguishing graphs with mass cut value 1 and mass cut value almost 1/2 plus epsilon requires omega root and memory in a single pass. And later this is improved to omega of n memory lower bound by Kapralov and Krachun. So this effectively says that in this interval, you cannot do anything non-trivial in terms of approximating mass cut in a single pass with polylog and space. And then people study multipass streaming, and it was proven by Assadi and N in 2021 that given any, so there exists an epsilon such that distinguishing mass cut value 1 and from graphs with mass cut value at most 1 minus epsilon requires polynomial space in multipass. So that left open the possibility that one might be able to do something non-trivial in terms of approximating mass cut in multipass streaming, just as is the case in polynomial time. Our work answers this question in a negative by showing that it is hard to distinguish graphs with mass cut value 1 with graphs with mass cut value at most 1/2 plus epsilon in polynomial space and constant number of proof outline of this result. The first part is to reduce this streaming model to a communication model. We can like we can divide the input tape into several segments and let each player take charge of each of the segments. And recall that there is a tape head that moves in this direction. And what we're going to do in the communication game is to first, when the tape head is at its leftmost point, we give the Turing machine to the first player. So the first player can simulate the Turing machine until the tape head completes the first segment and enters the second segment. By this point, the first player just throws the Turing machine memory to the second player. Because the memory is bounded by like n bits, so this process transmits at most n bits. And so on. When the tape head goes into the territory of the third player, the Turing machine is again thrown to the third player. That incurs n bits of communication. And when the tape head comes back to the left endpoint, finally there is a communication of n bits back to the first player. So in this way, we can view a p-task memory and streaming algorithm as a k-player communication protocol with total communication complexity p times k times n. Any questions at this point? And so since like the edges in the tape should form a graph, we're now going to specify what kind of inputs we're going to let each player see. So we're going to give each player a random matching on the underlying vertices. Even more than that, we're going to give them a random QXOR instance, which is like in the edges of the matching, we're going to add a label of 0 or 1. So each of these edges is now cannot be thought of as a 2 XOR equation that says that this variable and this variable must have an XOR value of 0. Given an XOR instance, we can transform it into a matching by taking only the edges where the labels are 1. So if we consider that there is an underlying solution to the whole system of XOR equations, then all those edges with 1 labeled are actually cut by this bipartition given by the solution. So in that case, we're going to have a max cut value of 1. But in a no case, if this system of random XOR equations does not have an underlying solution, if those labels are completely assigned at random, then the resulting graph is likely going to be far from bipartite. And because of all the randomness, it's going to have a max cut value of half plus epsilon. So we argue that in this communication model, it is going to take at least polynomial amount of communication to distinguish between the yes case and the no case reliably. We're going to get a bit more formal about this result, but on this informal level, is there any question at this point? Okay, so the next step is to formalize the communication game a little bit. we let this omega of U and M be the collection of all 2 XOR instances with U as the variable set, and then have like M disjoint equations. So it's like a label matching with, it's the set of all label matchings with M edges. So let's consider each of this input to one player. We can organize the collection of all 2 XOR instances and the collection of all underlying solutions into such a matrix. And for each equation and each solution, if the solution satisfies the system of equations, then we're going to put a 1 on this matrix entry. Otherwise, we're going to put a 0. So if we are given a solution, underlying solution, which is a bipartition, then we can look at the row in this matrix corresponding to that solution, and randomly pick one of the entries that is 1. And this will give us like a way to go from any solution to a random 2 XOR instance. So it's kind of like a Markov transition given by this right stochastic matrix. So this matrix, this 0, 1 matrix in itself is not really a right stochastic matrix, but we can normalize it by a fixed constant so that each row sums to 1, and this is exactly going to give you a way, the formal right stochastic matrix that specifies this Markov transition from the space of solutions to the space of all system equations. In a communication game, we're going to define there are k players, and each player will get a label matching y in this omega space. So the joint input space is going to be the Cartesian product of omega up to the k's power. We're going to put this matrix aside and consider the joint input space. So here I'm only drawing omega to the second power. Suppose the first player sent a bit of message, and it's going to divide the joint input space into 2 rectangles. And then the second player sends a bit, and then the first player sends another bit. Maybe this time so possibly the first player sent a bit or the second player sent a bit, but in any case, after m bits of total communication, the input space is going to be divided into 2 to the m rectangles, and on each of the rectangles, the players will decide whether to output 0 or 1. So this is the standard rectangle view of communication complexity. We're going to talk about the node distribution and yes distribution in this game. In the node distribution, we're basically thinking of the completely uniform distribution over the joint input space. But in a yes distribution, there's a random bipartition X, and then recall there's a Markov transition matrix. So this X defines this X is a row in the Markov transition matrix, and it defines a probability distribution over random instances. So each player gets an independent Y following this distribution. So this is like, now we have defined 2 probability distributions over this joint input space. And how do we measure the success of a communication protocol is to look at the total weight of the 0 rectangles or the 1 rectangles under the yes distribution or the no distribution. Yes.
Does this like do we have to think of this this row stochastic matrix, or are you not just drawing a uniformly random system that's satisfiable?
No, we have to like this formulation. First of all, this formulation is going to help with the analysis.
Okay.
But I think
like the 2 layers of randomness actually matter.
Yeah. So in the analysis, that I'm going to show,
okay,
this is going to provide a lot of convenience. But I think it's also important to emphasize that like there's one underlying solution that is distinguished.
It's like a null versus a planted.
I understand that, but like at least for nothing yet requires that there's a planted x. It just requires the existence of an x.
I mean, eventually he's going to show a lower bound for this particular. So he's just defining a problem.
Yeah.
To show a lower bound.
Actually, like the distribution you just asked about, like picking a random satisfiable system of equations. It's not immediately clear whether this distribution is the same as the distribution I'm talking about.
Oh, I see. Because you repeated solutions in some equation. Okay.
So this is like a mathematically more like at least well-defined distribution that is like at least easier to analyze. So any other questions at this point about the formally measuring the performance of communication protocols in this yes and no distributions? So the formal statement is that if alpha is a small enough constant, then any communication protocol having an advantage at least 0.1 must have total message length omega of n to the 1/3 over k squared. So next I'm going to talk about proof ideas for this communication lower bound. So for that I may want to use the whiteboard. Is it possible to lift this up?
Yeah, there's a button on the screen.
On the screen? Volume control.
You can also write on this side.
Maybe just right here.
Okay.
That might be better. Unless you want to write there. You can turn the system off. Are you going to need the slides again? Are you going to use the slides again?
I'm not going to use the slides.
Oh, okay. You can turn the system off entirely then. George can do it. Okay.
Oh yeah, that works. So I have just defined a right stochastic matrix. This is F2 to the U, and this is the omega space, which is a space of label matchings. It's a right stochastic matrix. I'm going to advertise equivalent view of this Markov transition that I think is provides a lot of convenience. I'm going to denote it by p tilde through n m. So remember that this is a Markov transition from F2 to the U. This is a space to the other space of omega m. Given any probability distribution here, the Markov transition is going to push that distribution forward to a probability distribution on this data space. But on the other hand, if we have a function, so this is the space of all functions on this space. If we have a function from this space to R, then for any function, we can pull this function back to a function on this space by this function acting on any input x is going to define by like the obvious. Is that clear? So now we can view this Markov transition as a operator, a linear operator between two vector spaces. Why does this view provide important convenience? It is because we can, the key is that we can do spectral analysis. On this operator. Let's say a bit more about this relation between this space and this space. So we can think of this as a graph between a bipartite graph. Let's say it's G. It's a bipartite graph with vertex at this. So there are two vertices. This is the left vertex set. This is the right vertex set. And there is also an edge set. Right? And this bipartite graph, the edge set is basically the satisfiable relation. Right? And it's not hard to see that this bipartite graph is a biregular bipartite graph. So this matrix is just a random walk matrix from the left side of the vertex set to the right side. And equivalently, there is a backward random walk from this vertex set to this vertex set.
Why is it biregular? Aren't there some are there some systems with many solutions and some with fewer?
Yeah, so recall that this is a very good question. We need to recall that this set of this space is the set of all instances that have m equations that are disjoint. So it must be a labeled matching.
Like a constraint graph isn't matching.
So every set of every equation in this space has exactly 2 to the n minus m solutions. Yeah, similarly from left to right. So this is the biregularity of this graph is the main reason why we choose like matchings, other than like random graphs. So we know that there's also a backward random walk, and the backward random walk is also going to give us a right stochastic matrix, but it's like with this as row and this as columns. And this is also the back random walk is also going to give us an operator. From this space to this space. And then we have a claim that this operator is exactly the adjoint this operator, in the sense that given any functions, pair of functions f and g, the inner product of f and g, so g is a function on the matching space, g is a function on the solution space, and f is a function on the matching space. So we can define an inner product on this space. This is equal to the inner product of these two functions on the matching space. This convenient property
provides some mathematical formalism that I think makes this operator viewpoint especially appealing. Now, having made all those basic preliminaries, we can go into the main analysis of this operator that we mainly care about. Let's talk about an important concept called hypercontractivity. Given an operator on a vector space, for example, let's say from the space of all functions on a space X to a space Y. What we mean by contractivity, if it contracts a norm, then it's saying something like T of F. The P norm of T of F is at most the P norm of F. Okay, but what is hypercontractivity? Hypercontractivity says that it not only contracts a given norm, but it also improves the norm. It says that T of F, the Q norm of T of F, is controlled by the P norm of F. And Q is larger than P. So it is well known that the LQ norm of is always at least the LP norm when Q is larger than P. So this hypercontractivity makes a kind of non-trivial statement says that not only is T contracting, but it also improves the norm. And this kind of hypercontractivity has proved to be widely that has been widely applied in discrete mathematics in general. And one of the main application in combinatorial, one of the combinatorial, I guess even like a combinatorial view of this hypercontractivity is about small set expansion. So again, let's think about a general bipartite graph between X and Y. So we have a left vertex set X, a right vertex set Y. Small set expansion says that if we have a small set in this X space and consider all the edges that emanating from X, there's going to be few collisions between those edges. And yeah, how do we, and now we're going to think about how we use the mathematical formalism to formalize this concept. So we can think about, so if this small set is called B, then we can think about probability density function defined by So why is this a probability density function? Is because for a random X, this is expectation usually value is 1. And one of those convenient properties of this operator viewpoint is that, so because this is a biregular graph, we naturally have a, let's say we naturally have an operator from, so this is a pullback operator from functions on Y to functions of X, and there's a push forward operator, P transpose, from functions on X to functions on Y. We can talk about the push forward of this probability density function. how do we measure the collisions of the emanating edges? We can measure the L2 norm of this push forward density function. And how do we we can formalize the intuitive concept of small set expansion into a statement of the form for any epsilon greater than 0, there exists a delta, constant delta greater than 0, such that let's say we're going to use the bipartite graph, the specific bipartite graph that we're going to care about as an example to formulate this kind of concept. So, the host, if we take B to be the host set here, then we're going to think of this scenario as the worst collision scenario. So this is the worst possible expansion in this bipartite graph. And in that case, if B is the host set, then the push forward of phi of B is just, if B is the host set, then phi of B is just a constant 1 function. And the push forward of the constant 1 function is still a constant 1 function. And we're going to have 1 here as the ratio. So we're going to say if this ratio here is much smaller than 1, then we're going to consider this as indicating a good small set expansion. So yeah, sorry. That is, I guess, how to make sense of this kind of mathematical statement. Any questions?
You're not saying anything about hyper, like you wrote the same 2 norm for both. So
Yeah, so I'm going to say how hypercontractivity can help you prove small set expansion. A hypercontractivity statement, on the other hand, so this is small set expansion. But what is hypercontractivity? Hypercontractivity is going to say that the 2 norm of this is at most, for example, the 5/4 norm of 5b. And what is this? This is basically the 2 norm of phi of b to the power of 2/5. So now you can see that if phi of b is if b the size of b is much smaller than whole set, then the 2 norm of phi of b is going to be pretty large. It's going to be much larger than 1. So this quantity is going to be much smaller than this quantity. And therefore, the hypercontractivity statement is going to imply the small set expansion statement. Okay, so we have finished talking about this small set expansion phenomenon. This is an important corollary of hypercontractivity. And in our case,
if you're going to, is small set expansion all you're going to need for the future steps you prove?
no, we're going to need something similar to small set expansion, but formally quite different.
Okay.
So there's the concept of randomness extractors in, I guess, widely used in theoretical computer science in general. And what is a kind of extractor statement? Extractor statement is to say that there exists a constant delta greater than 0, and we consider all subsets of the left-hand side. We're going to use this example as well, but this is completely general stuff. And if we consider a set that is large, previously we considered like small sets, but now we consider large sets that have density at least 2 to the minus delta fraction of the whole thing. Then we want this push forward to be very close to uniform distribution. So this should go to 0 as n to infinity. A distribution having like L2 norm, the density function having L2 norm very close to 1 is equivalent to say that this probability distribution is very close to uniform. People generally consider a good extractor as something that can extract a distribution here that is like that contains some information. It's not like completely uniform, very close to uniform, but we want it to extract to something that's pretty uniform here.
Why is it a less than or equal to then with the 1 plus the low 1? Why does that make it, I mean, it's getting close to, I thought you said the L2 norm being close to 1 is like the uniform, right?
Yeah, so L2 norm is at least 1 because L1 norm is 1, right? L1 norm is the expectation of the density function. So when L2 norm is very close to 1, it's going to be close to uniform. And this kind of extractor statement is not equivalent to the small set expansion statement, but unfortunately it can also be deduced from a hypercontractivity statement. Now we're going to talk about some real results about our the graphs of interest. This is proven by KKS in 14. This is like the single pass max cut lower bound of root n space. They show that suppose alpha is a constant like this, then for any function f, the push forward of f, the 2 norm is going to be controlled by 1 plus 1 over root n plus a small negligible factor. Basically, you can ignore this factor for all purposes.
Like the subscript is like the norm that you're taking of f?
Yes. This is something that's 1 plus small.
See, wait, and the plus is plus onto that or plus onto the, where are the parentheses again?
Oh yeah, sorry. This is this is one
I see,
sum n,
okay,
and this
okay,
is a sum
okay.
another sum. So ignoring this very small factor, basically this is a hypercontractivity statement. It says that this operator is a good hypercontractor. And as a corollary, it implies something much stronger than that. It actually implies something like for any constant 0, there exists a delta greater than 0 such that if B is at least, we can add even a root factor here, and still get epsilon here. Yeah, so this is how hypercontractivity statement can also imply small set can also imply extractor type statements. Yeah. So having talked all that much about this general relation between hypercontractivity, small set expansion, and extractor, let's revisit the yes distribution we have. In the yes distribution, we have an underlying planted solution, maybe X from this space. And it is going to go through a lot of those Markov transitions. So this is player 1, and this is player K. In a single pass streaming, we're going to, this extractor property proved by KKS says that whenever you have a distribution here on this space that contains some information but not much, but not too much, at most delta root and bits of information, then passing through each of this Markov transition, you are going to almost lose all the information. It's going to get to something that's pretty close to uniform. So if we think about this communication game, one player sees something and the other player sees something. So when the player I, the ith player, is going to say something, he looks at the previous messages, and previous messages translate to information on this space. When you pass through the number I Markov transition, it's still going to have very little information. So basically, this player, ith player, cannot, even based on previous delta n bits of information, it cannot distinguish between the yes distribution and the no distribution, because what he's going to see is still like close to uniform. This is how the single pass lower bound of KKS works. But for multi-pass lower bounds, this type of argument no longer works. And for multi-pass lower bounds, we're going to we're going to rely very much on the reverse direction. We're going to need to analyze what kind of information here is going to pull back to some non-trivial information here. So the natural question here is that is the reverse of this, the joint of this, the pullback operator that we started with, is this operator also hypercontracted? This is a concrete mathematical question that we can study, but unfortunately it is not. It is not hypercontracted. We can think about an interesting example. So we define some set A in this matching space, labeled matching space. So it's going to be the set of all labeled matchings that contains the edge 0, 1, sorry, 1 to 2. So, and also it has a label of 1 here. So this is a subset of this label matching space. And the uniform distribution on this space, on this set, pulls back to the uniform distribution on this. This is the uniform distribution on all solutions such that x1 plus x2 is 1. So this set is not really small, like it is like about like maybe 1 over n times the total space. But this distribution is far from uniform. So this example shows that we cannot hope for some extracted type of statement here without this transpose.
So A is still a small subset. It's like a 1 over n fraction.
It's a large subset. In extractor, we're going to talk about large subset. We want large subsets to extract to almost uniform distributions. But here is a large subset, but it does not extract to almost uniform distribution backward. So this example shows that the hypercontractivity fails for this operator.
But isn't A small? Isn't it only a 1 over n fraction of the...
Oh yeah, so 1 over n fraction is small if you only allow B to be like a constant fraction smaller than this. But for application purposes, especially like if you compare with the forward extractor, their parameter is like delta root n. So
without the root n, it would be bad.
it's 2 to the minus delta root n.
Okay.
So this factor like just says that how much information you're going to tolerate. Here you can tolerate delta root n bits of information and still extract to almost nothing. But there, this is like log n bits of information. So this is bad. And we're going to run out of time, but I don't have too much to say after that. But I'm going to show intuitively how to resolve this issue. The solution of this issue is a relatively new concept called global hypercontractivity. This concept was first developed in the theory of PCPs. This is by Kott, Winter, and Savra. They consider some graph called the Grassmann graph. This is a graph of significant interest in PCP theory. And they find that they want it to be a small set expander, but it fails to be a small set expander. And what they show is that they made the crucial discovery that what really drives expansion in this graph is not really it's having a small size, but it's pseudo-randomness, not small size, but pseudo-randomness. So there exists a mathematically well-defined notion of pseudo-randomness that allows them to say that although this graph is not a small set expander, but every pseudo-random set has near-perfect expansion. And it's natural to wonder here that because both extractor property and small set expansion are like downstream applications of hypercontractivity, is it also the case that we can sometimes prove that for large sets, if they are in addition pseudo-random, maybe although general large sets may fail to extract uniform distributions, if we add the condition of pseudo-randomness, maybe it does extract to close to uniform distributions. And that is exactly what we're going to achieve in this work. And yeah. Maybe I can say a few words about the notion of pseudo-randomness we're going to use. It's so we can talk about restrictions of this space. Given any, so this is kind of an restriction. You require like one of the coordinates of this y to be 1. And this set is bad because this set is not pseudo-random because after this single bit of restriction, the density of this set doubles, or like more than doubles. Is like because this set is only a 1/n fraction of this big set, so the density of this function enlarges by a large factor after you do this one single restriction. So this is considered bad for pseudo-randomness, and basically by a pseudo-random set we mean that any such restrictions do not enlarge the density of function of this set by a lot. And yeah, in other words, we're going to say that all counterexamples to the failure of hypercontractivity should look something like this. And that is going to give us like a mathematically controlled way to analyze what kind of non-trivial information the players can achieve to communicate. And because those information are structured enough, we can basically analyze the information flow by like combinatorial arguments. So yeah, I guess that's all I have to talk about proof ideas.